welcome to the Deep Dive. Today we're heading into a really fascinating comparison, looking at two, monumental achievements in ancient astronomy.
Yeah, it's like laying out two different blueprints for the universe side by side. See how they tackled the same problems.
Exactly, and we're focusing on Aryabhata from Gupta, India, and Claudius Ptolemy over in Roman Egypt.
Right. Figures separated by, a few centuries? And obviously different cultural backgrounds. Aryabhata around the 5th century CE, Ptolemy back in the 2nd century CE.
But facing similar challenges,
Yeah.
fundamentally. Both were working within a geocentric model. I mean, the idea that Earth is at the center.
Pretty much the standard view back then. And both used really sophisticated mathematics to try and predict how the planets and stars moved. Very impressive stuff.
Absolutely. They both wanted to map the heavens, figure out the patterns, predict where things would be. But, and this is our goal for this deep dive, their approaches were really quite different, weren't they?
Oh, fundamentally, in their methods, their assumptions, even their sort of scientific philosophy, you could say.
Yeah, I like the analogy you mentioned earlier, like two master clockmakers.
Right. Both building these complex machines to track the celestial bodies, both using gears, epicycles, difference in their models.
But with different designs, different ideas about how the central piece, the Earth, actually worked.
Exactly, and different mathematical tools they preferred.
And it's important to stress, I think, this isn't about saying, oh, this one was right and that one was wrong.
No, not at all. It's about appreciating the genius in both attempts to save the phenomena, as they used to say, making the models match what you actually see in the sky.
Okay, so we have these almost parallel worlds of scientific thought developing. Gupta, India, Roman Egypt, vastly different contexts.
Mm-hmm. And their major works reflect that you've got Aryabhata's Aryabhatiya and Ptolemy's Almagest. Different styles, different emphasis.
But both tackling the same core puzzle. How do you predict where the stars and planets are going to be?
That's the central challenge they both faced.
So where do their paths really start to diverge? What's a key difference right off the bat?
I think the most dramatic difference, arguably, is how they viewed the Earth itself. Aryabhata came up with this, revolutionary idea for the time.
You mean the Earth's rotation?
Exactly. He proposed that the Earth spins on its axis once a day, and that this spin is what makes it look like the stars and sun are moving across the sky from east to west.
Right. We talked about this in a previous deep dive on his Golapāda section. He had that analogy, didn't he?
Yes, the boat analogy. If you're on a boat moving smoothly forward, stationary things on the riverbank trees, houses, they appear to be moving backward.
So he's saying we're on this spinning Earth, and the fixed stars appear to move in the opposite direction.
Precisely. A really elegant explanation for the daily motion of the heavens. Quite a leap.
Okay, so that's Aryabhata. What about Ptolemy? How did he see the Earth's role?
Well, Ptolemy was firmly in the stationary Earth camp. He laid out his arguments quite systematically in the Almagest.
And these weren't just guesses, right? He had reasons based on the physics of his day.
Oh, definitely. He drew heavily on Aristotelian physics. The idea was that heavy things naturally fall towards the center of the universe.
Which, for them, was the Earth.
Right. So if the Earth itself were spinning rapidly, Ptolemy argued, how could an object dropped from a height fall straight down? Wouldn't it be left behind by the spinning motion? That was one line of reasoning.
Makes sense, given those physical assumptions. What else? Did he have observational arguments?
He did, or rather, arguments based on the lack of certain observations. He said, look, if the Earth is spinning incredibly fast towards the east...
we should feel a constant massive wind blowing from the east, right?
Exactly. A furious gale all the time. And since we clearly don't feel that...
Conclusion, Earth isn't spinning.
That was his logic. He also brought up things like birds and clouds. If the air wasn't carried perfectly along with a spinning Earth, wouldn't birds flying or clouds drifting appear to be swept drastically westward?
Or struggle to fly eastward at all.
Yeah. And just the sheer speed involved, the idea that the surface of the Earth at the equator would be moving at, hundreds of miles per hour seemed physically absurd to him and many others at the time. How can it hold together?
So putting the physics arguments and these observational points together.
Ptolemy's conclusion was clear and firm. The Earth is fixed, stationary, immobile, at the center of the cosmos.
And therefore, it must be the entire celestial sphere, the giant ball holding all the stars and planets.
That sphere must be physically rotating around the Earth once every day. That's what causes sunrise, sunset, the stars moving across the night sky.
Wow. That really is a fundamental split in understanding right at the core of their models. a spinning Earth versus a spinning heavens.
A huge difference in their foundational picture of the cosmos.
Okay, so given these completely different ideas about the Earth, how did they then tackle the more complex stuff like the planet's weird movements?
Ah, yes, the planets. They don't just move smoothly across the sky like the stars. They speed up, they slow down.
And sometimes they even seem to go backwards for a bit, that retrograde motion. That was a big puzzle.
A huge puzzle. Both systems needed ways to explain these irregularities. They both used the basic idea of epicycles, small circles, whose centers move along larger circles, the deferents.
That was kind of the standard toolkit for geocentric models, wasn't it?
It was the starting point. But Ptolemy found that simple epicycles and deferents centered on the Earth weren't quite enough to match the observations accurately, especially the changes in speed.
So he added more complexity.
He did. He introduced the idea of the eccentric, where the center of the main circle, the deferent, wasn't the Earth itself, but a point slightly offset from it.
Okay, that helps explain some variation. But wasn't there something else? The really famous or infamous addition.
Ah, you mean the equant. Yes. This was Ptolemy's real mathematical innovation for handling the non-uniform speeds.
Can you break down what the equant actually was? It sounds a bit abstract.
It is a bit. Imagine the main circular path. Now, picture a point. The equant, which is not the center of that circle, and it's not the Earth either. It's another offset point.
Okay, so another point floating in space near the center.
Pretty much. And Ptolemy proposed that the center of the epicycle, that little circle carrying the planet, moved along the deferent in such a way that its angular speed looked uniform only when viewed from this special equant point.
Not uniform as seen from Earth or from the actual center of the deferent circle.
No, only uniform as seen from the equant. Mathematically, this trick worked remarkably well. It allowed Ptolemy's model to predict planetary positions with, well, unprecedented accuracy for his era.
But you called it infamous earlier. Why did it cause problems later on?
Well, it came at a philosophical cost.
Yeah.
The whole Greek ideal, going back to Aristotle and Plato, was that celestial motions should be perfect, uniform circular motions centered ideally on the center of the universe.
And the equant broke that rule.
It did. The motion wasn't truly uniform around the center of the deferent. It was uniform only relative to this mathematical fudge point, the equant. It felt, to many later astronomers, like it violated the elegance and physical principles of perfect circular motion.
So it worked for predictions, but it felt less pure, maybe. Less physically real.
Something like that. It was a brilliant mathematical device for saving the phenomena, but it lacked that philosophical tidiness that many desired. It became a major point of contention later.
Interesting. Okay, so that's Ptolemy's intricate geometric machinery with eccentrics and equants. How did Aryabhata deal with the same problems of planetary speeds and retrograde motion? His approach was different, wasn't it?
Very different in emphasis, yes.
No.
If you read the Aryabhatiya, you don't find the same kind of detailed geometric descriptions of equants. Instead, his focus is much more on computational procedures.
The Manda and Śīghra corrections we've mentioned.
Exactly. These are terms for specific mathematical adjustments that needed to be applied to a planet's average position to get its true observed position. Manda relates more to the anomaly in speed, like what the eccentric quant addressed, and Śīghra relates more to the synodic anomaly, connected to retrograde motion and the planet's position relative to the sun.
So instead of drawing a picture with an equant point, he gives you mathematical rules.
Pretty much. He provides algorithms, often expressed concisely in verse, telling you how to calculate these corrections. You take the planet's average position, you use his sine tables, his Jaya values, and you follow these steps to compute the necessary adjustment, the phala.
And these calculations, they weren't always simple, right? Sometimes iterative.
Yes, often they involved iterative steps. You calculate a provisional correction, use that to refine the position, then maybe recalculate the correction, getting closer and closer to the final answer. It's a very computational mindset.
Now, does that mean he didn't think geometrically? Did he have some underlying model in mind?
That's a good question, and scholars debate the specifics. It's very likely he did have an underlying geometric model, probably involving epicycles and perhaps eccentrics. Later, Indian astronomers who built on his work certainly developed explicit epicyclic models.
But in his main text, the emphasis is different.
Exactly. The Aryabhatiya prioritizes the how-to, the algorithm, the calculation, the phala, or result. It doesn't dwell on visualizing the geometric machinery in the same way the Almagest does.
Which maybe points to the strengths of Indian mathematics at the time: algebra, algorithms, numerical methods.
I think that's a very strong possibility. We know this was a period of great advancement in those areas in India. Think of the development of the decimal system, zero sophisticated ways to solve equations like the Kukara method we discussed before. Aryabhata was a master of these computational techniques.
So Ptolemy builds this visible geometric clockwork, even if one gear, the equant, seems a bit odd.
Right. A very detailed mechanical drawing, you might say.
While Aryabhata gives you the instruction manual and the formulas to calculate the time precisely without necessarily showing you every single gear.
That's a pretty good way to put it. He leverages computational power to achieve similar predictive results, but through a different mathematical style, one that avoids an explicit device like the equant in his core presentation.
Fascinating contrast. Let's dig into those mathematical tools a bit more. Sines versus chords, geometry versus algorithms.
Yeah, this is really where their different backgrounds and preferences shine through. Ptolemy's Almagest is fundamentally a masterpiece of applied Euclidean geometry.
It relies heavily on geometric proofs, constructions, that whole Greek tradition.
Absolutely. And his core trigonometric tool was the chord. A chord is the straight line connecting 2 points on a circle's circumference. He constructed extensive tables listing the lengths of chords for different angles.
Which is related to our modern sine function, but not quite the same thing, right?
Exactly. It's related, but the calculations and approach are different. Ptolemy used these chords within his geometric framework to figure out angles and distances in his celestial models. It's all very visual, very proof-based.
You can almost imagine him with a compass and straight edge, working through the theorems.
Definitely that kind of feel. Now, Aryabhata, his mathematical toolkit feels much more, well, modern in some ways, even though it's ancient.
Because he used the sine function directly.
Yes. His jai, or more accurately, Ardha half-chord, is essentially the modern sine function. And crucially, he didn't just use it. He developed a method to calculate a highly accurate table of sine values.
That finite difference method we talked about previously, based on the property that the second differences of the sine values are proportional to the sines themselves.
Precisely that. A computationally sophisticated way to generate his fundamental table. And then his astronomical procedures are built around using these sine values within algorithms.
So less focus on geometric proof and more on calculation procedures.
Much more. His work is packed with algorithms for everything from solving equations to calculating those planetary corrections using his sine table. Think back to Kukara again. It's about finding a procedure to get the numerical answer.
So we have Ptolemy, the master geometer, using chords and proofs.
Building this logical visual structure.
And Aryabhata, the master calculator, using sines and algorithms.
Creating this powerful computational engine, it really suggests different ways of thinking about what it means to understand or model the universe. Is it about the geometric perfection of the model or the computational accuracy of the prediction?
Or maybe a bit of both, but with different priorities.
Perhaps. Their preferred tools certainly steered them down different, though equally brilliant paths.
Okay, so these two massive systems are built. What happens next? What was their legacy? How influential were they?
Well, this is where their stories diverge quite significantly again. Ptolemy's Almagest. Its influence was just immense.
Colossal.
It became the textbook. Pretty much the textbook for astronomy for, well, over 1,400 years. It was translated into Arabic, became the foundation of Islamic astronomy, which made further advancements, and then it was translated into Latin and dominated European thought through the Middle Ages right up to the Renaissance.
So people like Copernicus, when they started questioning the geocentric model.
They were reacting directly against Ptolemy. They had to engage with the Almagest, understand it, and then argue against its specific structures, like the equant, or its core premise of a stationary Earth. It set the agenda for centuries.
An incredibly dominant legacy. What about Aryabhata? Did his system, especially the rotating Earth idea, take hold in the same way?
Not really, no. At least not his specific cosmological model globally. As we touched on, even within India, the idea of a rotating Earth faced significant pushback.
You mentioned Gupta specifically.
Yes, Gupta, a major astronomer just a century later, wrote quite strongly against the Earth's rotation, using arguments somewhat similar to Ptolemy's, actually things falling straight down, etc. So Aryabhata's cosmology didn't sweep everyone away, even locally.
But, and this feels like a crucial but, his mathematical contributions had a different fate.
A profoundly different fate. While his specific model of the cosmos wasn't universally adopted, the mathematical tools he developed or refined were revolutionary and had a truly global impact, even if the transmission was indirect.
You mean things like the decimal system and zero?
Absolutely. The Hindu-Arabic numeral system, with its place value and the concept of zero, which were used by Aryabhata and were part of that Indian mathematical milieu, eventually traveled through the Islamic world to Europe and completely transformed calculation and science everywhere.
And his sine function, the algorithms.
Same story. The concept of the sine function, calculated accurately as Aryabhata did, and the emphasis on algorithmic computation were also transmitted via Islamic scholars. These became fundamental building blocks for trigonometry, for physics, for navigation, for essentially all of modern quantitative science. It's hard to overstate their importance.
So his cosmological picture didn't dominate, but his math changed the world.
In a nutshell, yes. And within India itself, his work, even with the criticisms, sparked a vibrant tradition. It set a high bar for computational astronomy that continued for centuries, leading to further innovations, refinements.
Like a Kerala school later on.
Exactly. Figures like Nilakantha Somayaji and others in the Kerala school critically engaged with Aryabhata's legacy, refined epicyclic models, and made incredible advances in mathematics, like infinite series for trigonometric functions, centuries before similar results in Europe. His work was a foundation, a catalyst.
So when we put it all together, comparing Aryabhata and Ptolemy isn't really about picking a winner.
Not at all. It's about seeing the sheer brilliance and, frankly, the diversity of ancient scientific thought. How these minds tackled the universe with the tools and ideas they had.
You get Ptolemy's incredibly influential, geometrically detailed universe that stood for ages.
The standard model for over a millennium.
And you get Aryabhata's computationally focused system with its groundbreaking mathematics and that radical idea of a spinning Earth, which maybe didn't win the cosmology debate immediately, but whose mathematical tools helped build the modern world.
It's a fantastic case study in how science progresses, sometimes through dominant paradigms, sometimes through revolutionary ideas that take time to percolate, and often through the quiet power of new mathematical tools.
And understanding this contrast really helps us appreciate the specific genius of Aryabhata and the Indian tradition, placing it in that wider global story of trying to figure out the cosmos.
It absolutely does. Which leads to maybe a final thought for you, the listener, to ponder. Just think about how those initial assumptions like, is the Earth spinning or still? And the choice of preferred tools, is geometry the key? Or is it computation? How these fundamental starting points can lead brilliant people to build such complex, sophisticated, yet ultimately different ways of understanding the very same sky above us, and how echoes of those ancient choices, those different paths, still resonate in how we approach science today.